So multiply by I, which is x here. We get what? We get, and what am I multiplying? Not the original differential equation, but the equation in standard form is what I'm multiplying. And so I get x dy dx plus y equals to x. Step 4 is to recognize that di dx is what? Di dx is actually equal to d dx of what? Of e to the integral of p dx. So what does that work out to? Well, that works out to e to the integral of p of x dx times the derivative of the integral of p of x, right? Dx. And that, well, anti-differentiation, differentiation, inverse processes, right? So that just gives me back p, and that's I. So this gives me IP. So what I'm trying to say here is, in general, the construction of the integrating factor is such that this just becomes I, oops, let me write that in not green because green doesn't show up, and I times di dx plus di dx times y equals to IQ, where I traded IP, right? I traded IP for what? For, come on, these are my markers. So all I did was exchange this IP for di dx because that's an identity, independent of p. This happens every single stupid time. So at that point, this becomes d dx of I times p. Excuse me, I times y equals to IQ. And at that point, we can just integrate both sides to finish the problem. I've run out of board space that half of you can see, so I better stop. But I can continue my example. So for the example, tilt your head and squint, you can see that that's actually d dx of x times y, which, by the way, is I times y in this example. And that's equal to x. So then how do I solve that differential equation? That differential equation we taught you how to solve like back in Calculus 1 when you first studied initial value problems. If you've got like y prime equals to a function of x, you just anti-differentiate. Y equals to antiderivative of the function of x. Fit the constant, right? So all I'm trying to say is integrate both sides. We're almost done. So integrate this is integral of this. So that gives me xy is equal to 1/2 x squared plus a constant. It's time for me to have a pointless heart-to-heart with you. When do we add the constant? At the end of the problem. We just forget about adding constants. And like some point at the end of the constant, at the end of the whole problem, let's say plus c, right? Because that's how it works. Is incorrect. We add the constant when the calculus demands it, which is right there. What we're going to see when we solve for y is that we don't have function plus constant. That constant will get intertwangled, if you allow me to use a technical term, with the function of x, right? Like, solve for y, what do you got? You've got y is equal to 1/2 x squared plus c divided by x. And that is your explicit general solution right there. I don't just, add c at the very end and ignore the fact that I actually have a c over x type term in my solution. And the same thing happens over here. Like in general, you integrate both sides, And so this leads us to the general, basically, result, which is that y is equal to 1 over the integrating factor times the integral of the integrating factor times q dx. There you go. That's kind of a general formula for the integrating factor problem. Now, the equation I just boxed in the upper left-hand corner is useless. You should not use it. It's a bad idea. How do you do the integrating factor method? You go through these steps. Why do you want to go through these steps and not just use the boxed equation up there? Here's the reason why. Because when we get to this step right here, which I'll put a red star over, that step, only works out. This step only actually works out for formulas that you derive if you calculated the integrating factor correctly. If you calculate the integrating factor, I, incorrectly, the reverse product rule will not happen for you. And that's your hint. Hey, you need to look at I again and fix it, right? If the reverse product rule doesn't actually make sense, you should actually think through this. Don't just assume it happens, think through it. And if it doesn't happen, that means you calculated I wrong. There's a redundancy, there's an error check in this method if you're willing to use it, all right? Any questions before I put another problem on the board? How would we find a specific value for C? Would that even make sense at the moment? I think at the moment the answer is no, wouldn't make sense. To find that constant, we need more data, right? So if you guys gave me some initial data, we could try to find it. Let's try it out. So, if y of 0 is equal to 6, then what do we want? We want 6. Oh, no. So 0. X equals to 0. Does this differential equation make sense as a differential equation at x equals to 0? Look at the original problem. What happens when you put x equal to 0? We've got 0 plus y equal to 0. I'm not sure that really, maybe I guess that forces y to be 0. There's just a point there maybe. Definitely the star equation has trouble with x equal to 0, right? So x equal to 0 is what's called a singular point for this differential equation. It's a point where our ideas about differential equations break down. So we should avoid 0 for this problem. I should give us initial data someplace more interesting, like 1. All right, let's do that. So y of 1 is 6. So 6 is equal to 1/2 plus c over 1, yeah? So that tells me that c is equal to 6 minus 1/2, also known as 11 over 2. And so my explicit solution is y is equal to, I'm going to do some algebra here if you don't mind. Actually, even if you mind, I'm still going to do it. 1/2 x plus 11 over 2x, I believe, would be the solution we want. So, you could do the algebra here. This is 1/2 x plus c over x, yeah? Please don't be the student in differential equations who does the following. What will make the teacher sad? Here's how to make your teacher sad. Do this. No. There's a c over here, but we have to divide both terms by x, right? You cannot cancel like that, just to be clear. If you were thinking that, keep that secret. Don't tell me. I don't want to know. All right, let's work another problem. So let's try to solve dy dx. Let's say y dy dx equal to x squared with point 1 comma minus 2 in the solution. All right. Oh, by the way, I mean, you probably, if you've never seen the integrating factor method before, you need to see more examples, right? So I do have a kabillion examples in my notes, I think. I forget exactly how many I left in this current version of notes, but if you start looking around my website, you'll find that I have dozens of these silly things worked out, right? So we'll work out another one before too long. I don't want to dwell on it at the moment. So I wanted to shift gears a little bit and just do a different example. This problem here is not an integrating factor method problem. In fact, that's kind of a useful point for me to make here. Not every problem's integrating factor, right? Not every problem's exact. Some are separation of variables, some are substitutions. Substitution more rare. Usually I'll tell you the substitution if it's a substitution problem. How about this one? This one, though, see, this is not integrating factor. Integrating factor, by the way, is linear. It's a linear ODE because the derivative and also the dependent variable y, they appear linearly. Yeah, the 1 over x is a nonlinear function, but when we talk about linear differential equations, we're talking about linearity of the dependent variable and its derivatives. So this, anything of this form is a so-called linear first order ODE, all right? And the integrating factor method can be used to solve every linear first order ODE, given continuity of the functions, of course, but all right, let me get to it. We're about out of time. So we got y dy equals to x squared dx. Yeah, integrate. Whoop, 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 whoop. 1/2 y squared is equal to 1/3 x cubed plus a constant, which gives me that y squared is equal to 2/3 x cubed plus twice that constant, right? And so what does that give me? That gives me y is equal to plus or minus, yeah? 2/3 x cubed plus 2 constants, right? The plus or minus generally depends on which one you choose, depends on what's your initial data, right? So I gave us the initial data 1 minus 2, which means that minus 2 is equal to plus or minus the square root of, well, 2/3 plus 2c, right? So there's no choice in the matter. We have to choose what? We have to choose the minus solution because of that data. And then you can square both sides. We get ourselves 4 is equal to 2/3 plus 2c. So apparently 2c is equal to what? 4 minus 2/3, also known as 10/3. And so there you go. My explicit solution here is y is equal to minus, the minus is important, square root of 2/3 x cubed plus 10/3. And there you go. That's the solution to this problem. We should check it. Does it actually work? When we plug in, uh-oh, it's not going to work. What did I do? No, I just solved for 2c. See what you're saying? Haha, pun intended. But I'm an idiot. It's horrible. Horrible, horrible, horrible. X equals to 1, we get 2/3 plus 10/3, which is, what is it? 4? Oh, good. And what's the square root of 4? 2. That's good. So 1 spits out minus 2. Is this minus up for, should there be a plus minus on the solution? No. If you write plus minus on the solution on the test, do I take points off? Historically, yes. I take points off 40% of this class for this issue on the first test, almost every single semester. Don't be that class. I've said this before, though. It does no effect. There's still a third of you are going to make this mistake. I mean, it's going to happen. It's just an actuarial fact, if you believe in that sort of thing. All right. Thanks, guys. Next class, more differential equations. Woo.